Okay, so two things in this lesson. The first is I'm going to give you a formula for variance. So let's kind of pick up where we left off. In the last lesson, the definition of variance is that the variance of x is the expected value of x minus its own expected value squared. Um, and that definition is good for understanding the logic behind the concept. Even if it has some steps and took some unpacking, you could sort of see how it made sense that we would want to think about, if we want to think about how uncertain a random variable is, thinking about how, on average, its distance from its expected value, how large that is, squared distance. That would be a good way to think about how risky a situation is. It's actually not the most common way we write down variance for formulas, for proofs, for calculations. What we typically do is we rearrange this expression into something that's easier to work with. So I want to start with this and get you to the formula that we use all the time. So, like I said, let's start with this. Start with what we have, x minus x bar. No, start with writing it the right way. Put that square in the right place. That's critical to what we're doing right now. X bar squared. Okay. Just starting with the definition there. The first thing I'm going to do is I'm going to multiply out that square term. So just not skipping steps here. I've got x minus x bar times x minus x bar here. And all I'm doing is just doing the multiplication inside the expectation operator. So I'm working on these this function of the random variable. I'm rewriting it. So it's x squared minus 2 x bar times x plus x bar squared. Okay, so I'm just multiplying out there. And a thing I want to remind you of, because it's critical for following what I'm doing here and so many more similar arguments that we're going to see in the coming weeks, it is critical to remember that this x bar is just a number. Okay? It's a number that happens to be the expected value of x, but in terms of mathematically, we can treat it just like a constant, the way we do a and b in the a times ex plus b function there. And so what that also means is that x without the bar is a random variable, and that we have to be more careful with, okay, because it has a more fiddly set of algebraic rules for the random variable as opposed to the number that is its expected value. Okay, so bearing that in mind, that plain x, random variable, x bar is a number, let's see what we can do here. Well, first of all, what we've got is the expectation sign hitting what I'm going to call a sum. It's like it's a negative sign here, but it's a negative constant, the sum of three things. And we showed in the workshop from the last lesson that workshop, we show that the expectation of x plus y, two random variables, is the expectation of x plus the expectation of y. So another kind of exception to the general rule, another case where we can just distribute the expectation operator when it's a sum. So we're allowed to do that here, and we're going to. So I can just take the expectation operator through x squared minus the expectation of 2 x bar x plus the expectation of x bar squared. So all I've done in this step is I've taken this expectation operator inside the parentheses, or inside the sum is the way people would think about it. I've distributed it. So the expectation of this plus this plus this is that expectation plus that expectation plus that expectation. And that's, we showed, is always okay to do. Okay, so going along, not much I can do with the expectation of x squared. That just is what it is. But now looking at the next term, so 2 is a constant. I can pull that outside of the expectation operator. But so is x bar, right? I keep saying x bar is just a number here. So we can, it's just like a in the ax plus b. So we can pull it outside. That's what I'm going to do. Okay. So the expectation of the number 2x bar times random variable x is that number 2x bar times the expectation of x by itself. Okay. So this is, again, this is where the rabbit goes in the hat. So I'm really emphasizing this. This is just like expectation of ax here, and now I have a times the expectation of x. That's all I did. Okay, and okay, now let's look at this last term. I have the expectation of x bar squared. Well, that's just a number. So the expected value of a constant is that constant. Expectation sign goes away. So again, let's stop and make sure that we understand what happened in this last step here. Nothing happened with regard to the first term. It just stayed what it is. The second term, we pulled the constant that included the expected value because the expected value is a number and a number is a constant. It's not a random variable anymore. So we can just pull it outside of the expectation sign, and we're left with just this x, no bar on it. So it really is a random variable. And the expectations operator is only operating on it now. That's what we did in the middle term. That's kind of where most of the action was, but there was also something that went on with this last term where we just said, okay, well here, this thing that we're taking expected value of, not really a random variable. It's just a number. The expected value of 5 is 5. That's all that went on here. All right. One more thing. Next step. You might notice here that we've got x bar and we've got the expected value of x. Those are the same thing, right? We've just got two different ways of writing the same thing. Let's remind ourselves that that's just a notation thing. So at this point, it's not super helpful to be using the two notations. Let's just replace the e to the x with x bar. Let's keep doing it in black here. So still, that first term stays the way it is. This is 2x bar times x bar plus x bar squared. Oh, look at that. This is squared minus 2x bar squared plus x bar squared. Okay, so negative 2x bar squared plus x bar squared, that's just negative x bar squared. Remember, these are all, the x bar is just a number here. So the final step is minus, no, I'll write it the other way. Sorry, I said I was going to use the x bar notation, so I'll keep on doing that. That's the formula for a variance that you may remember from other classes that you've taken that we're going to use extensively going forward. And you will see it written the other way as well. And this formula for a variance will remind you, if you forget, that it matters whether you square the random variable and take its expectation, or you take the expectation and square it. Okay, those two things, this will be different numbers, and so the variance will be a number. Another thing about variance, just to bear in mind, because it's not totally obvious from this formula that we use over and over again. We started from something, the expected value of a random variable that is a square that only takes positive values. Variances can only be positive. If you do some calculations and you get a variance that's negative, something went wrong. Okay, so that's a fact to remember. It's very easy to make mistakes in calculations. But this formula here is the way we will normally be writing variance. It just came from doing algebra on this definition that we started with. You could probably even start with it as a definition. It's just, as I said before, harder to see the logic in my mind when variance is written this way than when it's the expected value of squared distance of the mean. Okay, so that's thing one here. The other thing that I want to talk about just briefly in this lesson is standard deviation. So if you know the variance, you know the standard deviation, because the standard deviation is the square root of the variance of x. Okay. Sometimes we write the variance of x as sigma squared. This is another way to write the variance. It kind of goes along with the mu notation for expected value. And when we write the variance that way, it's kind of natural to write the standard deviation as sigma without the square. Okay. You'll also see people writing just standard deviation, writing it out in abbreviated form, just kind of the way we do with variance here. Why would we want to take the square root of the variance? Taking square roots generally makes things more complicated. It's a pain, and we don't do it when we're doing any kind of sort of probability or statistics, any sort of like analytics to explain why we are treating our data the way we are, why we're doing what we're doing to our data. So you use variance, you're going to be using variance in your methods classes all the time. Standard deviation, though, is helpful in applied statistics. We actually have numbers that mean something to you in terms of a substantive problem, because standard deviation comes with units that make sense. As I said in a previous lesson, that variance doesn't really have units, or if they do, they're the square of the thing that you started with. In general, variance isn't helpful to think about the actual magnitude of the number. But if you want to do that, take the square root, and the standard deviation will be measured in the same units as your outcome. That's also true for the expected value, right? So if you have a random variable where the outcomes are coming up in dollars, the expected value is going to be in terms of dollars, and the standard deviation will also be in terms of dollars. Or if it's height in inches, all those outcomes are measured in inches, the expected value is going to be in inches, and the standard deviation will also be in inches. And people will often report, just when they're sort of trying to describe a collection of numbers, sometimes they'll report the standard deviation, or sometimes they'll report a range of values that's kind of meant to capture, like, where's most of the data, or is where are most of the outcomes associated for this random variable. And a kind of conventional way to do that is to say, what is 2 standard deviations from the mean? Okay, so if we had a height example where the mean height was, say, 66 inches, and let's say that the variance here, the variance of, let me sort of be clear about what the random variable I'm talking about here. The random variable is the height of a person drawn at random from a group. Okay, the mean is the expected value of that. The variance of that would just, we could calculate the variance as well. And let's say the variance was 9. I'm going to say the mean is 6 inches. I'm not putting units on the variance because it's not inches. It's just better to not think about units with variance. But if I want to take the square root of variance and get 3, the standard deviation again is 3 inches. Okay, so what we might say in this case is 2 deviations from mean corresponds to a range of 66 plus or minus 2 standard deviation. Each standard deviation is 3 inches. So this would be a range of 60 to 72 inches. And giving a little bit ahead here, but not too far ahead, for random variables that make sense to model using a normal distribution, which height would be one. Many things do sort of approximately fit a normal distribution. In those cases, the probability that x is within 2 standard deviations of the mean is roughly 0.95. So that's kind of just a nice rule of thumb. It's a useful fact about the normal distribution. So if you hear about something that could be normally distributed and somebody is just, all they're telling you about it is the mean and the standard deviation, a way to sort of wrap your brain around, well, what are we talking about here, is to add and subtract 2 times the standard deviation from that mean value, and 95% of the time, the random variable is going to come out in roughly that range. Okay. As I said, standard deviation is very useful for talking about actual data where you care about the actual numbers, the magnitudes that you're getting, and so you are going to be using that in your empirical work. For classes like this, methods classes, where you're going to be learning how to do the statistics that produce the numbers in your empirical work, variance is the main thing that we're going to be working with. Okay.